Hello, ladies and gentlemen. Welcome to our webinar. We will start at point of 14 o'clock. Please wait a little bit. Okay, I think it's 14 o'clock. Ladies and gentlemen, welcome to our webinar under the title MEMS Technologies in Dresden. My name is Johannes Kade and I'm responsible for business development in IPMS, especially in the field of medical devices and systems. May I introduce my colleague, Mr. Fritz Herrmann. He will give you an overview about the technological possibilities of IPMS Dresden and its cleanroom facilities. Fritz Herrmann is a technical sales manager in our engineering and manufacturing department. He holds a diploma degree from the Technical University in Dresden in the field of industrial engineering. And he has special experiences in CMOS-based ultrasonic transducers. Please be so kind and ask your questions in the service area of the GoToWebinar application. So Fritz, now it's your turn. Please start with your paper.
Thank you, Johannes. So welcome, ladies and gentlemen, to my webinar about the MEMS Technologies Dresden. I want to share with you some insights about our clean room and what we do at IPMS in the field of MEMS devices on 200 millimeters. And to give you an idea what we are talking about, I have on this slide our vision, what we are targeting. And that is in particular the customized solutions in the field of MEMS. What does it mean? We as the members of IPMS and the drivers of the clean room are experienced with the technologies in the field of MEMS, and we are experts in those kind of technologies and do the process development for MEMS-based devices. I wrote down here experience with technologies transfers from in and ex MEMS clean rooms. That means that we transfer technologies from outside of our clean room into our clean room. For example, when you think about of a startup that has an idea about a device which they want to get miniaturized and scaled up, then we are the partner to get those devices built up in our clean room. X of our clean room means that we are, if it's a process that is working and we do it in a kind of a pilot fabrication, we can transfer those technologies into high volume fabs to scale up functional devices. What is very important and often gets misunderstood when people think and hear about IPMS, we are a research institute, but we work at very high level industrial standards, and we are close to industrial fabs or foundries with our clean room and the environment around it. And to give a brief introduce to the Fraunhofer Association or Society for those who are not familiar with Fraunhofer. Fraunhofer is the biggest organization in Europe for applied research. So we are not basically doing fundamental research, we're doing applied research. The whole Fraunhofer Society has more than 25,000 people working there as staff and is divided into 72 institutes or research units. And we are, as IPMS, one of those institutes in the field of MEMS, but all other, let's say, topics around industry are covered by the Fraunhofer Society. The entire Society of Fraunhofer has more than 2.3 billion euros as financial volume. This is quite a large number, and you can target a lot of research topics with that. Now I will go more deeper into the history of IPMS as an institute. We became independent in 2003. And later on, 4 years later, we decided to build up our own MEMS clean room because the demand was so high in those researches. And this resulted also in the inclusion of the Fraunhofer CNT, which became in 2013 a department of the IPMS. And they are doing slightly different things to the 200 millimeter clean room. They have an extra facility, but I will go more into detail a bit later about this. So the last years we had a big change in our clean room. We transitioned from 150 to 200 millimeters, and this was completed in 2018 with the first lot of a core technology, which got finally and successfully finished. In 2019, nearly every product and technology was transferred, and so we are now running completely on 200 millimeters. The next big step for us is in 2021. So the next big step for the clean room, let's say it like this, is in 2021, when we start our DUV cluster, where we try to approach much smaller pattern sizes and resolutions for our devices. But also more about this later in the presentation. Also some figures about the IPMS. We're growing very, very well. The last 5 years were a big growing, and now we are nearly with 450 employees and students which are working for and at the IPMS. This means we have technicians, engineers, students, PhDs, who are all working in the field of microelectronics and MEMS devices. Our budget was grown in the last years to this year around 50 million euros, which is quite a large number. And how is this budget based on? We are 25% funded on a basic funding by the Fraunhofer Society. 25% are done by public funding from the government and the so-called Länder here in Germany. And the main part by far is the direct industrial contracts, and this is what we are mainly focusing on, the contracts with our customers to develop and process things together with our customers. On the next slide, there's an idea about what kind of applications we are targeting in this, let's say, new world. These three fields are often used, and these are industrial solutions. So everything which is around industry is also done with parts of our devices. Quality of life is another field of application which we are targeting, and medical and health. What is also sometimes misunderstood, that we are not doing the products itself in our clean room. Obviously, we are doing devices that enable those kind of products. So if you see the fingerprint sensor here in the middle, This is just an idea how devices of our clean room could be used in the later stages. But we don't build smartphones including these devices. We are just the developer and supplier for those kind of devices. But what kind of devices, you may ask, are these that the Fraunhofer IPMS is developing and producing? Here are some topics, what we do with our clean room and what is built up in our clean room. I just want to highlight some because the list is long. And one of our biggest topics is for sure, or are for sure, the spatial light modulators, where IPMS is very famous for in the world, because we integrate thousands and millions of micromirrors and get them acting very reliable. Also, what we do is, as Johannes mentioned, which was my field the last couple of years, technology-wise, were the CMOS, which are growing in their market share. And those CMOS are used for a big variety of applications. Nearly every field of application I showed recently, you can use CMOS, and yeah. Also, what we are very famous for is our MEMS scanning mirrors. Those devices are becoming popular, especially in the automotive industry, for lighter applications where you can guide lasers, and it's a very interesting topic. I'm interested myself in how this field is going in the future, and so may you be excited with me too. All these other things we will see in the presentation, in the further slides. So if you have some particular interests, contact me or answer a question. Yeah. So the next thing I want to share with you is what I call portfolio technology matrix. We have on the one hand side the field of applications, and we have on the other hand side the technologies we are running in the clean room. I will come to the technologies right after this slide, but to give you an idea how these devices I recently showed, like CMOS, are used in applications, this is what I want to show you in this slide. For example, when you think about a surface micromachined CMOS or SLMs, they could be used in, I already talked about the CMOS that are used, for example, for gesture recognition or fingerprint sensors. They could be used. And also in the field of medical devices, we have a partner working together, a startup from the US called Autonexus, where we are working on a medical CMOS, where you can recognize if a child has a middle ear infection based on viral or bacterial, and based on this information you can give antibiotics or not. And this is clearly something that is enabled by our device and put together into a bigger picture with the medical application. In the field of bulk micromachining, I already said that things like LiDAR are very important and interesting for also the industry. When you think about logistics centers where robots driving around, they have to get an idea about their environment. And so if they have an idea about their environment, which could be done with those kind of micromirrors and the LiDAR system behind, this is clearly an approach and a field of application for those bulk micromachined micromirrors. And what is very interesting also is the micro speaker that was invented of a technology that was invented at IPMS, which is called nano e-drive. I will go more into detail on this technology later in my presentation, but right this year we had the spin-off, which is called Arioso, where those micro speakers getting into mass production and focusing on consumer markets. So a very interesting story coming out of IPMS, and this shows how the basic principle of IPMS is working. We think about new innovative technologies and approaches. We prove them, we bring them into pilot fabrication, and once it is proven and we are focusing for mass production, we can transfer it either to a high volume fab or we can transfer it into a spin-off. Yes. Also, what is based on the nano e-drive is our micro pumps or micro valves. I will also have this technology later on in my slides, so that I'm not going more into detail right now. In the field of active silicon, we do produce or develop and manufacture ESFETs for pH sensing. There are a huge variety of applications that you can target with. Yes. When you think about the integration from MEMS and CMOS, that's a huge topic. How you act with those MEMS devices, and the highest integration density you obviously get when you integrate it on CMOS directly. And this is what we are focusing, what we have been put in focus the last years. And now we are able to integrate MEMS on CMOS, or we are able to offer modules to contact CMOS from external partners and get surfaces either on roughness or material wise that are our customers asking for, because the high volume fabs like X-Fab have their standard products, and it's sometimes difficult for smaller companies to get their top surface on a CMOS with what they want. And we do also run projects where we get exactly those interconnection to MEMS or other devices on top of a CMOS. Same procedure is for bolometers or thermopiles that we also have in our repertoire. So let's dive more into what we physically do in the MEMS clean room. When you think about all these applications, there are technologies behind it, and the fabrication of these technologies have let's say two different approaches. I have 4 modules, but let's say there are 2 basic technologies or 2 basic approaches. And this is on the one hand side the surface micromachining, which is for our devices used for spatial light modulators or CMOS, so the capacitive micromachine ultrasound transducers. And how does it work in principle? I have this brief animation, and you have to imagine that you have a plain or bare silicon wafer. On top you get your first layer. Let's take, for this example or for this animation, a metal. On top of the metal you deposit your sacrificial layer. This sacrificial layer gets patterned. After you pattern this layer, you deposit your last layer or your top layer. And once this is done, you release the sacrificial layer, as the name calls it, and etch it out of the substrate, so that you get actor spaces or plane actor spaces or a cavity. There are different approaches for this sacrificial layer technologies, and we do use amorphous silicon or silicon oxide, which we release with xenon difluoride or hydrogen acid. Yeah, this approach needs some very specific tools and a specific tool park. And we try to cover all these things, and we are very successful, with, especially with our SLMs and CMOS. And here you see the small or an overview about the capabilities that are needed and that we are covering with our tool park. For example, the deposition of the amorphous silicon. But what is very important for this technology is for sure the gas phase etching, because you have to get rid of the sacrificial layer. And what is also important for us in the last years is the anti-stiction functionalization of our devices, which we typically do with an ALD or MLD monolayer deposition tool from SPDS. Where we deposit 1.4 nanometer FTTS, so that we get very hydrophobic surfaces, which is needed to prevent sticking in the later on usage. We do this on chip level, but typically we do it in a batch reactor with our 200 millimeter wafers, and what is needed is the reduction for the contact forces, because when you think about mirrors or CMOS and they are bending, and once they touch the bottom layer, then you need to prevent that they are going to pull in, and this is more or less done with those kind of approaches. Another technology approach, when we leave the surface micromachining for a while behind us, is the bulk micromachining. This is another approach. You try to get 3D dimensions with, yeah, it's nearly based on a very high aspect ratio etching, which is done like you deposit a patterning on top of your silicon, and then you etch the silicon with very high aspect ratios into the silicon. You see on the right side a micro mirror on the top, and right below there is the comp drive that drives this micro mirror. And these comp drives are typically done with bulk micromachining, and this is a very challenging process, but we managed to get those processes handled, and we are focusing on getting up to 40, or aspect ratios up to 40, to get those movements done. It's used for what I already said for the micromirrors, but it's also used for this technology approach of nano e-drives, which I'm going to focus more in the next slides. But before we do this, I'm also trying to give an overview about how these bulk micromachined devices are getting built up. There are also very specific tools needed. For example, we bought a grinder for thinning, and the topic of BSOI is a very complicated topic in the field of MEMS, and right now it's really hard to get those BSOI wafers. But yeah, I will also say something about this in the following slides. But what I'm trying to say is here with this slide, this is a very complex process, especially the deep silicon etch, and this is over years we managed to get those processes very reliable, and our devices are working very good with those approaches. As I said, we recently bought a grinding tool, and the way we are focusing, or why we did this, is that we have a high demand for our technologies on wafer thinning, but also what we focusing on in the future is the preparation of BSOI wafers, because as I said, it's really hard to get BSOI wafers, especially with the specifications you're looking for. Within months, it takes nearly half a year or a year to get BSOI wafers, and even then you have to compromise and don't get exactly the specifications we are looking for. And we try to close this gap in our clean room in the way that we try to build up our BSOI wafers on our own with functional patterns or capabilities built in. But this is on the next slide. About the grinding tool, which is also important when you think about sustainability. We try to reclaim our wafers on our own, and this is therefore a grinding tool is also very important and makes it easier for us to get our own wafers reclaimed. What is also very significant to this grinding tool is that when you look around, you not often find CMOS compatible grinders, but we try to approach that, and we are focusing on a CMOS compatible grinding tool. On the next slide, what I already mentioned, we are right now building our own BSOI wafers for, first of all, internally applications and devices, but also once this is working well for us, we also provide this to our customers, and we have different scenarios we are focusing on, and this is on the one hand side, in addition to the grinding tool, that we try to focus on different wafer thickness. As we know, the requirements are very different, and we had also different requirements to the suppliers of BSOI wafers, and so we figured out that it would be the best to get the right thickness on our own with the grinding and the CMP tool. What we also think about is doing BSOI wafers with already doped wafers, depending on request. And what is new, or what is good for us, and probably also for our customers and their devices, is the integration of cavities or buried metallization or other things on those wafers. And yeah, we did tests in the past, and we are very happy with the results so far, and we go on this way. And it should help a lot also with our own technologies. For example, the nano E-drive technology, where we also think about when you think about customized BSOIs, stacking up multiple wafers to get much bigger integration on these BSOI wafers. Now I'm on the point where I want to talk about the nano E-drive, which is an actuation principle which was invented at the IPMS. more or less, you have a cantilever, and this is the gray one in the animation, and this cantilever is divided by a spacer to a top electrode, and you can bend the cantilever by getting the top electrode in charge. And what is revolutionary to this actuation principle is that you focus on large forces with those cantilevers by a very low power consumption, and this makes it very interesting for a lot of applications which we are driving. And I already showed you some, for example, the Nano eDrive micro speaker, which becomes the spin-off now. And yeah, let's go into detail of the Nano eDrive applications. Here you see a few that we already running. For example, the ultrasonic transducer approach with microphones, where you can get done gesture recognition and distance recognition. On the other hand side, things like Internet of Voice or Internet of Things, which you maybe know from Amazon Echo. This is also something we try to address and try to figure out how this actuation principle could be working with. And also the so-called positioning platforms. I have a video soon where I can show you our recent results, and it's very promising what we did there. Also, microvalves and micropumps are things that are very important for the medicine of the future, and we are very promising that our devices can help there a lot. Here you see the micro positioning chip with an inchworm system based on Nano eDrive. You have here the simulation and the idea. What do we try to focus on? I think I don't have to explain a lot. The video, first the video of the animation, what we tried to figure, and then afterwards what we achieved is very promising, and it shows how what opportunities the Nano eDrive gives us and our customers. So when we get to the video, I hope it will work now. Here we have the video where you see on the right side you get the movement upwards, and on the left side you get the movement downwards. It's a bit plastical here, but I think the next video shows much better what is what we try to achieve and what we actually achieved in the last months. And here you see that this platform goes up by the movement with the Nano eDrive, and you move up, 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 and later on you move down. And what we just achieved with this demonstrator right now is that we can get this platform deflected by 1 millimeter with a low power consumption, and that's pretty cool that it works right away and is done by this actuation principle. If we go ahead, we also, what I said, build up ESFETs, which we put into the field of active silicon. It's not the only field where we address or what we built in this soil of technology approach. We also do silicon photodiodes, but I'm not getting more into detail to this topic right now. But what is important is that we build up our own CMOS, and we have our own CMOS process for one of our devices, where we, and this is the last soil, where we integrate our own build-up CMOS, or where we build our own devices on top of our own CMOS. For this soil, there are other technical parts important, for example, the deposition of active layer like tantalum pentoxide, or the TMAH backside opening to get those backside opened. And also what is very important for this technologies is the trimming and the knowledge about the thermal oxide, which we use as gate oxides in these technologies, which is a bit outstanding compared to our other technologies. But since we work in this field also for many years, we have a great knowledge about this this technology approach. Yeah, the MEMS and CMOS is always, I already said a lot about this, because this is something that is also important, I think, in the future, to get on the one hand side, shorten time to market by the parallel development of CMOS and MEMS devices. And what is also interesting to this field is that you get higher densities on the wafer in integration with this approach. And it's very hard, because the requirements for the top levels of the CMOS to get high precise MEMS devices working is very high. And so this is by far not an easy process and an easy module. But since we used to work in this field for the last years to get our MEMS and CMOS integrated, we have also great knowledge there. And right now I'm responsible in a project where we used to interconnect a CMOS wafer for an external partner, that they can get on top their device done. And the requirements to the top level planarity, for example, is huge, and also getting the interconnection done is not that easy. So yeah, this is where we're focusing on, and what we did in the past, and where we improved a lot in the last couple of years, which was also or where we could also increase, because we bought a 5-zone CMP with the transition onto 200 millimeters, where you can get really flat surfaces on top, for example, of a CMOS wafer, because you can planarize in 5 different zones of the wafer to get the planarity you're targeting on. To summarize this, let's say, capital, I have here a brief summary about the 4 approaches we are focusing on in the MEMS clean room here in Dresden. And this is combined with surface micromachining, bulk micromachining, active silicon, and MEMS and CMOS, which you can more or less combine with each other. For example, the nano E-drive technology could be built up in a surface micromachine way, but also in a bulk micromachine way, which is depending on in which direction more or less you want to get the cantilever moved, either in X or Y direction. Next, I want to show you or give you an idea of how we cooperate with our partners together As I said, we don't do the products itself here in Dresden at the clean room. We work with partners again that are having a product in mind, and we more or less support our customers with MEMS devices, and in this particular case with Heimann Sensors and the X-Fab that are both located here in Dresden. We have a very close collaboration, and this results in a I think almost 10-year collaboration where we do the MEMS supplement and do research and development in some specific processes, but also we are a facility partner for Heimann Sensors, or they are for us, because they have parts and some equipments in our clean room. And compared with the knowledge of the CMOS manufacturing of the X-Fab, we have a good cooperation to get a successful product placed, and now into multiple iterations increased over years. Now to get a bit deeper into where we do this and how we do this, I want to share with you this slide, which shows what we exactly targeting. So when I say we are working not on a product like Heimann, then this means we are doing the device. This I already said too, but from which to which point we do this. So we do the research and feasibility studies in the first way when a customer, for example, or we as an institute say the nano e-drive is a cool principle. We first of all try to figure out, is this a principle and is this working in the way we think of or our customer thinks of? And once this is proven and the processes, the basic processes are developed, we try to put them onto a level where these things become a demonstrator or prototype, which was shown some years ago that the nano e-drive as an actuation principle is working, and is also working on wafer level design. And this leads into the phase where you think about what can you do with these devices, in which fields you can address them, and then you get their diversity. And later on, you can scale up into pilot fabrication. As I said, when you think about the micro speakers of Arioso, they think about larger numbers of devices and not just a principal study. And this is what we also do and what we also have done multiple times in the past. And what is sometimes interesting for partners that work with us together, because they think we are not a big factory or big foundry, but what we can do is we can transfer to those foundries once the process flow for a device is frozen, and this is what we covering with our 200 millimeter MEMS clean room here in this facility. On the other hand side, we also have a facility on 300 millimeters, which is called the CNT. It's nearby. Right now, we are sharing a clean room with Infineon, and this is also this gives an idea. This is not a pure MEMS clean room. They have other research topics. For example, neuromorphic computing is a big topic for the future there, and working together with big companies like Infineon or Bosch or Global Foundries to develop their processes and getting material screening done. To get more into detail about the 200 millimeter MEMS line here in Dresden, I already tried to give you a hint that we are working very close to industrial standards, and I think these points that I show here prove me right, I guess, because we can do the R&D and pilot fabrication. And what is very important compared to other foundries, we don't do really high volumes, meaning by millions of chips, but we do thousands of chips and multiple wafers in one technology. But what we try to focus on is the low volume, high mix. So as you have seen in the slide where I showed which topics we are researching on, we have so many different technologies and devices that this is called for such kind of a fab, a high mix. We are working in a 24/5 3-shift operations mode. This also shows how many things we driving through the clean room with our almost 90 people on staff that running this clean room. Right now we have a 400 nanometer I-line stepper or 365 nanometer I-line stepper, but we will increase the limits, or we go to the limits with the next step in 2021 with the DUV cluster. And yeah, all these other facts like CMOS compatible and ISO 4 and the ISO 9001 certification, all these things are a proof that we're working on a very high industrial level, and that we are not like in university working with low contamination standards. We can build devices on the top level. This slide I will pass. As Johannes said, you will get my slides afterwards. Here's just to give you an idea. We do cover all processes of MEMS building and the fabrication for MEMS manufacturing, like deposition, oxidation, lithography, and so on. So if you have particular requests, please do afterwards or contact me directly. Yeah, the DUV and the lithography are always the core of a fabrication, of a MEMS fabrication. And as I said, the I-line stepper we do have, but we also have a double-side mask aligner. And as I said, in 2021, we are focusing on getting our DUV cluster online and work in another dimension, much smaller dimension and resolution than we do nowadays in the field of MEMS. What comes together with the DUV cluster is also the measurement and the overlay. So double checking what you have done with the DUV tools and the scanner, and there we increase a lot with our metrology tools. Not only in the lithography, but also measuring everything we do with our MEMS devices to get reliable and high quality devices done, which is needed on the one hand side by our own devices, but also for the devices of our customers. What we also cover is not only the build-up of MEMS, but also the back-end assembly, which includes the dicing, the pick and placing, and also the packaging in the end. As I said, we try to increase our capabilities in the field of bonding. We do cover a big variety of bonding approaches, which is needed nowadays, and which is a good base for our SOI designs and the fabrication of those BSOI wafers. What is also important, even not only in the field of MEMS, but even in micro systems and microchip development is the testing and the characterization of what you have done. We have devices that have run multiple months through our clean room, and so we have to have a very high standard of testing those devices and get the highest yields for us and our customers. In the end, this is almost my last slide. We do also we do also collaborate with other Fraunhofer institutes, which are combined in the FMD to substitute each other and to build or to have backup processes that we maybe not cover. For example, back end of line modules like copper deposition or TSVs. We don't cover these, but we do have a close connection to institutes where we have those backups. And if we cover 80 or 90% of our customers' requirements, we can get back to our network to get the last 5 or 10% also for our wafers or our devices or the devices of our customers. And last but not least, I want to share with you an insight of our clean room. Hopefully, yeah, this will. So this was my presentation about the MEMS technologies Dresden, and this was my webinar. I hope you enjoyed it, and if you have requests or questions, please feel free to ask me or Johannes, and yeah, thank you.
Okay. Thank you very much for your presentation. Ladies and gentlemen, now we are open for your questions. I hope I can see some question or some ideas in the service area. In the meantime, a question from my side to Fritz. Fritz, what could you describe? What could be the best reason for mutual projects with IPMS with a customer? What is the real bargain or the advantage in such a partnership?
That's a good question for sure. I think we are in the environment of high tech, and we focus on improve and we focus on innovation. And I think what we cover very good is the high flexibility that foundries that are very big cannot achieve or cannot offer their customers. What I said when I introduced our clean room, this low volume, high mix approach is a good thing for our customers, because we have a deep insight in a lot of technologies, and we can cover many problems and challenges from other technologies, and get this experience into the products of our customers. So this is, I think, a big advantage, and what typically is an approach for startups to come to us and say, hey, we have a brilliant idea, like Ottonexus, they came to us and said, we have an idea, but we cannot go to let's say X-FAB because there's no frozen process. The processes are not frozen, and so stabilize your processes, and then we can think about a mass production, because low volume requests are also not often done by high volume fabs, because it's not efficient for them. Yeah.
Thank you. Fritz, please describe for our customers or for the attendees of this webinar how we manage the customer and the project idea, IP. Sorry.
So you mean when customers have IPs or have a process or a product and they come to us?
Yes, look, a customer comes and say, okay, we want to go in a mutual project, and we have some IP. How could it protect it?
Yeah.
And the other hand is how could the IP be protected inside of the project results?
Yeah. Okay, I see. Yeah, so we always do NDAs with our customers, and once a customer has an idea or has a process or has IP on its own, we are just we just provide to build these things, but we don't use the IP in other projects. So in the past, what we had, a project where I was part of, was a technology transfer from a university in the United States, and they had a process, and the company said, we bought this process and we want to get this process done in a clean room, which is feasible for in their case, high volume with a high yield and a good quality, which is often not feasible for a clean room in a university environment. And this was the case this was the case, and they handed us over the process flow. We did it, and later on they promoted the product with the device, which was built by us, but the IP is always in the hands of our customers in these kind of scenarios.
Okay, thank you very much. Ladies and gentlemen, if there are not any questions more, then
I think there are questions.
Well, I can't see. I can't see. Oh, so yeah. Do you have any experience in growing and etching silicon carbide?
No, we had not yet. I'm not sure about the CNT. I can ask for this.
We can give you a written answer by email, and we will have a look at this topic. Fritz, which type of thick SOI do you use?
Which type of
thick SOI?
How thick our SOIs are? Is that the question?
I think so. Or which type?
Which type? So the doping.
I think so. Thickness, he said.
The thickness.
I think this down from standard.
So yeah, we don't have a standard thickness like this. now we try to focus in the first iteration for standard BSOI thicknesses, but later on we want to focus much thicker SOIs. That's the reason why I said we try to bond standard wafers doubled or twice, because we have some approaches where this is needed, and it is really demanding, or it is really important what the customer requires. It's not a fixed range where we what we target. So if there's a specific request, I can double check that, but I cannot say we do it from 400 microns to 1.5 microns thickness. So there's a lot of potential in the thickness as well for the device as also for the target layers.
Okay. There's another question, Fritz, how the stress and thickness of the deposed layers will be measured. Please give an overview about our measurement systems.
Yeah, we do. Most likely we use ellipsometry. We do use a lot of reflectometry for oxides, for example. Metals, of course, are a bit harder, but you can measure those with, for example, AFMs. Or what we also do sometimes in getting our etch results screened, we do SEM or FIB cuts. So SEM analysis or FIB cuts to analyze the thickness of the targets, as well as we have a very hard so-called test wafers where we test very often the deposition rates of our tools, so we can estimate once there's a request for, let's say, 1000 nanometers of I don't know, amorphous silicon. We can either measure them with typically ellipsometry, or we can also double check it with our experience of the deposition rate, which we hardly control.
Okay, thank you. Yeah. Another question: do you have vibration energy harvesting technologies for the development? I think it is more a question for our CNT. I'm sure we have, but not in our 200 millimeter line.
I know there are approaches, but I think I'm not allowed to talk about this because this is in early stages, and this is in combination with a partner of ours, and so I know there are investigations in this field, but not that I can bring it off here.
Okay, another one. Just a second. Oh, it's a little bit complicated. Do we have an idea on optical parameters? Just a second, for calculation of the metal layers.
Yeah, we do have. We also measure them in a lot of fields, especially for our mirror devices. We measure the reflectance, and we also track them sometimes directly while the deposition of the tool, which is on the one hand side used for the deposition of the layers, but or for the tracking of the layers. But yeah, we track in particular technologies and products the reflectance of the metal layers. For example, aluminum or Titan, aluminum. These are typical deposited layers, and there we track it very closely because we have obviously when you build up mirrors and you use them for example in lighter applications or something like this, or you're focused to use them in light applications, you have to reach reflectances that fit for this application, and then it's necessary to know what kind of reflectances you have.
Okay. Another question. Do you have, just a second, do you have any ion slicing technique capability for thin film piezo transfer methodologies?
What was the first one? Ion?
Ion slicing technique capability. I think no.
No.
We can say in short no. Okay. So the designing of the metal coatings. So I think that this. I think we have answered on all the questions we have seen here in the service area of the GoToWebinar application. If there are additional questions, don't hesitate to ask questions under the email address from Fritz Hermann or from me. Yes, and from my side and from Fritz Hermann's side, many thanks for your attention. Have a nice day, and I hope we can come in contact in the next time. Many thanks.
See you. Bye-bye.
Bye-bye.